In this video, we're going to talk about Cauchy integral formula. This formula is amazing. It is beautiful, it is powerful, and it has far-reaching consequences. It will change the way you think about complex integration as a whole. Let's jump right to it and see where it takes us. Okay, so let me describe the formula. So let's say we have some domain D, which is simply connected domain, bounded by piecewise smooth curve gamma. So let's say D is that, and we'll orient ourselves counterclockwise around this domain D. And for the function f, it needs to be analytic on the boundary of D as well. So let's say we're sitting inside of domain U, where the function itself is analytics, and that the U has to cover the boundary of the set D. Okay, so let's say we're integrating along the outside of the domain D. This formula is true. So the function evaluated at any point W inside of D, let's say that point is D, W, you could actually evaluate the function by not looking at the function there, only looking at the function along the outside of D, or the boundary of D. So you integrate along the boundary of D, you get to evaluate the function inside at W. With some constant 2 pi I involved. Okay, so I just want to say this is incredible. That means that the function, any analytic function, contains all the information about the function inside just by looking at the boundary. So this kind of tells you how restrictive this condition of being analytic is. Because once you define a function along a curve around the region, that tells you how the function has to behave inside. There's no more choices after that. Okay, let's look at the proof on why this might be true. Okay, so let's pick a point W inside of the domain, and we'll pick an epsilon that's small positive number, and we'll look at some like a disk of radius epsilon around that point W. Okay, let's actually compute the integration. So we can integrate along curve gamma, but because if we use the Cauchy's theorem, we can kind of think of this as a flexible rubber band path, right? So we'll just shrink that path down to the boundary of this small disk. Okay, we should have the same path integral. Let's actually compute it. All right, so we're going to, so the center is at W and radius is epsilon. So gamma epsilon defined by this formula right here from 0 to 2 pi will trace the outer boundary of the disk of radius epsilon around W. Okay, so that goes in place of Z in the formula for the Cauchy's integration formula. Note that the W here and minus W in the denominator cancels out. And the derivative of this curve, gamma epsilon, is given right here. Okay. And then if you look, the I will cancel out with the I in the front of the integral. And epsilon et, e to the it, and epsilon e to the it in the denominator also cancels out. So only thing that's left is 1 over 2 pi on the outside with integration from 0 to 2 pi, and inside is f of w plus e to the, sorry, epsilon e to the it. Now, f is analytic, so it's also continuous, which means if epsilon is very small, this value is very close to f of w. In the limit, it'll just be f of w. So you were integrating pretty much the constant f of w from 0 to 2 pi, and we're dividing by 2 pi. So we're just going to get f of w. And that's exactly what we wanted to prove, right? This formula gives us f of w. All right, let's do a couple examples quickly. So let's say I want to integrate this integral, and we're integrating on the boundary of the circle of radius 2, centered at the origin. Okay, so if you look at a circle of radius 2 around the origin, it contains this point 3/2, which is the w in this Cauchy's integral formula right here. So I'm thinking of z squared is my f, and 3/2 is my w. Now, this doesn't quite look like the formula yet, because it's missing 1 over 2 pi I in the front. But we could just multiply and divide by 2 pi I. So if 1 over 2 pi I does not exist in the front of the integral, then that means that I just have to multiply my answer by 2 pi I to make up for the fact that 1 over 2 pi I didn't exist, right? So the formula tells us that the integral is going to be 2 pi I times the function evaluated at the w. So z squared evaluated at 3/2. That's what we have here, 3/2 squared. So if you square it, we're going to get 9/4. The 2 and 4 in the denominator will reduce, and we get 9/2 pi I. Okay, so I hope that computation made sense. If we integrated around the unit circle, circle radius 1, then now 3/2 is outside of the unit circle. So in that case, you could just shrink the curve down to a point, and that tells us that the integral is equal to 0, right? That's just by using the fundamental theorem of analytic functions, we'll just get 0. So it does have to, the curve has to contain the point w in the inside. Okay, one more example. So let's say we want to evaluate this path integral. So the numerator here, this is my f of z, and w is not written here, but z in the denominator is same thing as z minus 0. So we can think of the w as 0. And 1 over 2 pi I is missing in front of the integral. So I'm just going to multiply the answer by 2 pi I first. And what I have left is log of z plus pi, where I plug in the value 0 into z. So I just get log of pi. And that's it. And you do have to be careful. We have to have a analytic function on this unit circle. But if you look at the function log of z plus pi, remember log function is usually defined on a slit plane, where the origin is undefined maybe usually we take the negative real axis as a kind of slit so that we have a single valued function defined. But if you have z plus pi, that will shift all the domain to the left by pi units. So the domain of log of z plus pi is actually looking like this. Okay, which is nice because if we integrate along the unit curve, the function is analytic throughout the important region we care about. So we could still apply the Cauchy integral formula and we get the result that we have there. So it is important to check that our function f is analytic in the domain that we care about. Okay, all right. We're going to push this formula a little bit. So here's a theorem that I want to prove. If f is analytic in an open set U, then f prime is also analytic in U. If you try to understand what this theorem is saying, so analytic means that you have a function that's differentiable, right? And if it's saying that f prime is also analytic, that means that the derivative also has a derivative, which means that the second derivative also has a derivative by repeated use of this theorem. And we can conclude that once you have an analytic function, it's infinitely differentiable. If you can prove that you have one derivative in a complex sense, then you have as many derivatives as you like, which sounds like an insane conclusion. It's certainly not true in the real function sense. Like you could have a function that's maybe twice differentiable, but not the third time. With complex functions, you just need one derivative, and you have derivatives forever. So let's see how we might prove something like this. It seems too good to be true, but here's how to prove it. Okay, so let's look at f prime, and we're gonna see if we can compute the difference quotient limit. So that's what we would have. I'm gonna use the letters alpha and w here. Okay, so the function f and f of alpha and f of w in the numerator, I'm going to rewrite those using Cauchy integral formula. So here's what we get. Okay, so the first one we're using alpha as our w, and the second function of w is taking the place of w in the formula. And then everything is divided by alpha minus w. Okay, let's get the common denominator and add the fractions in the inside, at the top, I mean. So z minus alpha and z minus w are different factors. So you could multiply top and bottom on the first fraction by z minus w, and we're going to multiply the second fraction by z minus alpha over z minus alpha, and we could subtract. So this is what we get here if we combine. And alpha minus w, that comes from dividing everything by alpha minus w. That's the same thing as multiplying by 1 over alpha minus w. So we're just going to squeeze that in the bottom as well. Okay. And if you kind of try to simplify the numerator, f of z times z and f of z times z cancels out. And f of z times w does not cancel out. Sorry, I have to write everything out. So f of z times z minus f of z times w minus f of z times z, these cancel out, and plus f of z times alpha. Okay, so in the numerator, basically we have f of z times alpha minus w. But this is great because we have alpha minus w on the bottom. We can cancel out, right? So let's just do that. If we do that, we just have f of z on the top and z minus alpha and z minus w on the bottom. But now that we write it this way, we canceled out the division by 0 we get from putting alpha and w closer and closer together. We're taking the limit as alpha goes to w, and now there's no division by 0 if we take the limit. So we can just plug it right in. So the alpha now becomes w. So we have z minus w squared on the denominator. And here's basically the Cauchy's integral formula for the derivative, right? So f prime of w could be written like this, which is very reminiscent of Cauchy integral formula, except that we have the power 2 there. Let's see. Okay, sorry, I had to pause the recording. Let's get right back to it. Okay, so what we've done so far is written the derivative in this very Cauchy integral formula type of formula with just different exponent 2 there. We could actually repeat this exact same algebraic computation over and over again. So we could actually write down the formula for f double prime, f triple prime in very much the same way, which is incredible. So here's the new version of Cauchy integral formula that also takes care of derivatives as well. So, okay, let's say you have a simply connected domain D bounded by a piecewise smooth curve gamma, and F is analytic on some set that's bigger than the boundary. Then we get this formula. So not only that this is true for analytic functions, you could actually compute any derivative of the function by using Cauchy integral formula. Like we don't even have to compute the intermediate derivatives. You just need the value of the function along the boundary. And then you just divide by a different power of z minus w. And that'll give us up to a constant, the kth derivative of that function. So you can take derivatives by integrating. Okay, so let's see this in action. So here's some formula, g squared times sine of z over z minus pi cubed. Okay, so I'm looking at this. I'm gonna take the numerator, f of z times sine of z, that's my f. My w is going to be pi. Okay, and because the exponent is equal to 3, that means that we're going to look at the second derivative of the function, right? And also the 2 pi I, we don't have the division by 2 pi I, so we multiply by 2 pi I. We didn't have a multiplication by 2 factorial, so we're going to divide by 2 factorial. And what's left when we use this formula is that we're going to have the second derivative of this guy evaluated at pi. So we do have to take derivative, but in general, taking derivative is way easier than integrating. So I don't mind that too much. So here's the first derivative, here's the second derivative, and we plug in z equals to pi. And sine of pi is 0. So the first and the third term drops out. And we just have 4 times pi times cosine of pi is -1. So we'll get a negative sign. So we just have 4 times pi, and there's also already a pi in the front. So -4 pi squared I. And that's That's it. We're computing these integrals by looking at derivatives. Here's another one. This one's a little bit easier. Let's see. So my f is e to the z. My w is -1 here because I'm subtracting the w. And because the exponent is 2, that means we're looking at the first derivative, right? We take the exponent, subtract 1, and that's how many derivatives we have to take. So it's 2 pi I divided by 1 factorial. 1 factorial is just 1. Take the derivative of e to the z, which is e to the z, and then we plug in -1. So we get 1 over e, 2 pi I over e. Okay, so it's very satisfying formula to use. I think it's pretty cool formula, but it actually has some very far-reaching consequences as well. So we'll take care of that in the next video. See you later.